A main distribution panel, or MDP, with a main breaker rated at 400 amps can indeed have a branch breaker also rated at 400 amps. To understand this, we need to delve into the National Electrical Code, specifically Article 240.6 and 240.100c. Article 240.6 generally states that the ampere rating of a branch circuit should not exceed the ampere rating of the branch circuit protective device. This is a fundamental principle ensuring that the circuit's wiring and connected equipment are adequately protected from overcurrents. However, like many rules, there are exceptions. Article 240.100c provides a crucial exception in the scenario. It states that where the branch circuit protective device is a circuit breaker rated at 400 amperes or less, the maximum rating of the branch circuit shall be 400 amperes. This exception acknowledges practical applications where a large branch circuit, such as one feeding a substantial load like a large water heater, requires a protective device of this size. In the situation presented, a water heater requires a 400 amp breaker and the main distribution panel itself is rated for 400 amps. Because of the exception found in 240.100c, it is permissible to install a 400 amp branch breaker in this main distribution panel. To further clarify, let's consider what overcurrent protection aims to achieve. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can lead to overheating, insulation damage, and potentially fires. The NEC establishes standards for the selection and installation of these devices to ensure safety and prevent electrical hazards. The NEC is not intended to hinder or restrict normal operations, it simply exists to reduce the risk of catastrophic failure. When evaluating the safety of an electrical installation, several factors must be taken into consideration. Firstly, the ampacity of the conductors must be sufficient to carry the intended load. Ampacity refers to the current carrying capacity of a conductor, and it is determined by factors such as the conductor material, size, insulation type, and ambient temperature. Secondly, the overcurrent protection device must be properly sized to protect the conductors. The overcurrent protection device should have an ampere rating that is equal to or less than the ampacity of the conductors it is protecting. Thirdly, the equipment connected to the branch circuit must be suitable for the intended use and must be properly protected. Equipment should be listed or labeled for the intended application, and it should be installed in accordance with the manufacturer's instructions. Returning to the scenario of a 400 amp main distribution panel feeding a 400 amp branch circuit, several considerations come into play. Firstly, it is important to verify that the main distribution panel is properly rated for the intended load. The main distribution panel should have a sufficient ampere rating to handle the combined load of all the branch circuits connected to it, including the 400 amp water heater circuit. Secondly, the conductors feeding the 400 amp branch circuit must be properly sized to carry the load. The conductors should have an ampacity of at least 400 amps, and they should be installed in accordance with the NEC requirements for conductor sizing and installation. Thirdly, the 400 amp breaker must be properly selected and installed. The breaker should be listed or labeled for use in the main distribution panel, and it should have an interrupting rating sufficient to handle the available fault current at the installation. Fault current is the amount of current that would flow in the event of a short circuit or ground fault. The interrupting rating of a circuit breaker is the maximum amount of fault current that the breaker can safely interrupt. If the available fault current exceeds the interrupting rating of the breaker could fail to interrupt the fault, which could result in equipment damage, injury, or even death. In addition to these considerations, it is important to ensure that the installation complies with all other applicable requirements of the NEC and any local codes or regulations. Electrical codes are constantly evolving to address new technologies and safety concerns. It is the responsibility of the electrical designer and installer to stay up to date on the latest code requirements and to ensure that all installations comply with these requirements. The NEC also provides guidance on the proper selection and installation of electrical equipment. For example, Article 110.3b requires that listed or labeled equipment be installed and used in accordance with any instructions included in the listing or labeling. This requirement helps to ensure that equipment is installed and used safely and effectively. Another important aspect of electrical safety is proper grounding. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and clear the fault. The NEC provides detailed requirements for grounding electrical systems and equipment. These requirements are designed to minimize the risk of electric shock and to protect equipment from damage. Regular inspections and maintenance are also essential for ensuring electrical safety. Electrical systems should be inspected periodically to identify any potential hazards or problems. Maintenance should be performed as needed to correct any deficiencies and to keep the system in good working order. By following these practices, it is possible to create a safe and reliable electrical installation. Now let's consider some additional scenarios related to main distribution panels and branch circuits. Suppose the main distribution panel is rated for 600 amps instead of 400 amps. In this case, the 400 amp branch breaker would still be permissible, provided that all other requirements are met. The main distribution panel would have sufficient capacity to handle the 400 amp branch circuit, and the conductors and overcurrent protection devices would need to be properly sized and installed. On the other hand, suppose the water heater requires a 500 amp breaker instead of a 400 amp breaker. In this case, it would not be permissible to install a 500 amp branch breaker in a 400 amp main distribution panel. The main distribution panel would not have sufficient capacity to handle the 500 amp branch circuit, and the installation would violate the NEC requirements for overcurrent protection. In this situation, it would be necessary to upgrade the main distribution panel to a higher ampere rating or to find a different way to supply power to the water heater. Perhaps the water heater could be replaced with a smaller unit that requires less power, or perhaps a separate sub-pump could be installed to feed the water heater. In any case, it is important to ensure that the electrical installation complies with all applicable requirements of the NEC and any local codes or regulations. Furthermore, it is essential to understand the difference between the terms ampere rating and ampacity. Ampere rating refers to the maximum amount of current that a device or piece of equipment is designed to carry continuously without overheating or failing. Ampacity, on the other hand, refers to the current carrying capacity of a conductor under specific conditions. The ampacity of a conductor is determined by factors such as the conductor material, size, insulation type, and ambient temperature. The NEC provides tables and guidelines for determining the ampacity of conductors under various conditions. It is important to select conductors with an ampacity that is equal to or greater than the ampere rating of the circuit or equipment they are feeding. This helps to ensure that the conductors will not overheat or fail under normal operating conditions. In addition to selecting conductors with the proper ampacity, it is also important to protect them from physical damage. Conductors should be installed in a way that minimizes the risk of abrasion, impact, or other types of damage. This may involve using conduit, raceways, or other protective measures. Conductors should also be properly supported and secured to prevent them from sagging or pulling on connections. Another important consideration is voltage drop. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or fail, and it can also reduce the efficiency of the electrical system. The NEC provides guidelines for limiting voltage drop in branch circuits and feeders. These guidelines recommend that the voltage drop in a branch circuit should not exceed 3%, and the voltage drop in a feeder should not exceed 5%. To minimize voltage drop, it is important to select conductors that are large enough for the intended load and to keep circuit lengths as short as possible. In some cases, it may also be necessary to use voltage boosting equipment to compensate for voltage drop. In summary, installing a 400 amp branch breaker in a 400 amp main distribution panel is permissible under the NEC, provided that all other requirements are met. It is essential to verify that the main distribution panel is properly rated for the intended load, that the conductors feeding the branch circuit are properly sized, and that the overcurrent protection devices are properly selected and installed. It is also important to comply with all other applicable requirements of the NEC and any local codes or regulations. Electrical installations should be inspected and maintained regularly to ensure safety and reliability. By following these practices, it is possible to create a safe and efficient electrical system. Furthermore, it's crucial to understand the concept of selective coordination in overcurrent protection. Selective coordination means that in the event of a fault, only the overcurrent device closest to the fault should trip, leaving the rest of the system operational. This is important in critical applications where a power outage can have serious consequences. Achieving selective coordination requires careful selection and coordination of overcurrent devices. The devices must be sized and adjusted so that the downstream device trips before the upstream device. The NEC provides guidance on selective coordination in Article 240.12. This article requires that overcurrent devices be selectively coordinated in certain applications, such as essential electrical systems in hospitals and emergency systems in other facilities. The NEC also addresses the use of surge protective devices, or SPDs. SPD are designed to protect electrical equipment from voltage surges, such as those caused by lightning or switching operations. Voltage surges can damage sensitive electronic equipment and can also pose a fire hazard. SPD are installed in parallel with the electrical system, and they divert surge current to ground. The NEC provides requirements for the installation of SPD in Article 285. These requirements specify the types of SPD that are permitted, the locations where they must be installed, and the wiring methods that must be used. It is important to select SPD that are appropriate for the voltage and current levels of the electrical system and to install them in accordance with the manufacturer's instructions. The NEC also addresses the issue of arc fault circuit interrupters, or ASIs. ASIs are designed to protect against arc faults, which are dangerous electrical conditions that can cause fires. Arc faults occur when electricity jumps between two conductors, creating a high-temperature arc. These arcs can ignite nearby combustible materials such as wood, paper, or fabric. ASIs are designed to detect arc faults and to interrupt the circuit before a fire can start. The NEC requires the use of ASIs in certain locations, such as bedrooms, living rooms, and dining rooms. These requirements are intended to reduce the risk of electrical fires in homes and other buildings. In addition to these specific requirements, the NEC also contains general requirements for electrical safety. These requirements cover a wide range of topics such as wiring methods, grounding, overcurrent protection, and equipment installation. The general requirements are intended to provide a baseline level of safety for all electrical installations. It is important to be familiar with these requirements and to follow them carefully when designing and installing electrical systems. The NEC is updated every 3 years, so it is important to stay up to date on the latest changes. The NEC is available for purchase from the National Fire Protection Association, and it is also available online. Many states and local jurisdictions adopt the NEC as their electrical code, so it is important to check with your local authorities to determine which version of the NEC is in effect in your area. In addition to the NEC, there are other standards and guidelines that may be applicable to electrical installations. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standard Institute, or ANSI. These standards provide more detailed information on specific aspects of electrical design and installation. It is important to be aware of these standards and to follow them when applicable. Electrical safety is a shared responsibility. Electrical designers, installers, inspectors, and users all have a role to play in ensuring that electrical systems are safe and reliable. By working together and following the requirements of the NEC and other applicable standards, it is possible to create a safe and efficient electrical environment. Let's consider some further implications of having a 400 amp main breaker and a 400 amp branch breaker. The main distribution panel's busbar rating is critical. The busbar is the metallic strip inside the panel that distributes power to the breakers. Its rating must be at least 400 amps and preferably higher to safely handle the potential current flow. If the busbar is underrated, it can overheat and create a fire hazard. The service entrance conductors, which bring power from the utility to the main distribution panel, must also be sized appropriately. Their ampacity must be at least 400 amps, and they must be protected by an overcurrent device typically located at the service entrance. The grounding system is another vital component. A properly installed grounding system provides a low impedance path for fault current, helping to clear faults quickly and safely. The grounding electrode conductor, which connects the grounding system to the earth, must be sized according to the NEC guidelines. The equipment grounding conductors, which connect the metal enclosures of electrical equipment to the grounding system, must also be sized appropriately. Coordination studies are sometimes required for larger electrical systems. A coordination study is an engineering analysis that determines the proper settings for overcurrent devices to ensure selective coordination. The study helps to identify potential coordination problems and to optimize the system's protection. Arc flash hazard analysis is another important consideration, particularly in industrial and commercial settings. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit or ground fault creates an arc of electricity. The arc can generate intense heat and pressure, causing serious burns and other injuries. An arc flash hazard analysis assesses the potential risks of arc flash and recommends measures to mitigate those risks. These measures may include using arc-resistant equipment, implementing lockout/tagout procedures, and providing personal protective equipment for workers. Proper labeling of electrical equipment is essential for safety. The main distribution panel, branch circuit breakers, and other electrical components should be clearly labeled to identify their function and rating. This helps to prevent accidental contact with energized parts and to ensure that equipment is used properly. Electrical safety training is crucial for anyone who works with or around electricity. Training should cover topics such as electrical hazards, safe work practices, personal protective equipment, and emergency procedures. Employees should be trained to recognize and avoid electrical hazards and to respond appropriately in the event of an electrical incident. Regular inspections and maintenance are vital for maintaining the safety and reliability of electrical systems. Inspection should be performed by qualified electrical professionals who can identify potential problems and recommend corrective actions. Maintenance should include tasks such as tightening connections, cleaning equipment, and testing overcurrent devices. Keeping accurate records of inspections, maintenance, and repairs is important for tracking the performance of the electrical system and for identifying trends or patterns. These records can be used to improve the system's reliability and to prevent future problems. Electrical safety is a continuous process that requires ongoing attention and effort. By following the guidelines and requirements of the NEC and other applicable standards, and by implementing sound safety practices, it is possible to create a safe and reliable electrical environment. The 400 amp branch breaker situation, while permissible under specific NEC exceptions, necessitates a thorough evaluation of the entire electrical system to ensure safety and compliance. Always consult with qualified electrical professionals for design, installation, and maintenance of electrical systems. They have the knowledge and experience to ensure that the system is safe, reliable, and code compliant. Remember that electrical codes and standards are constantly evolving, so it is essential to stay up to date on the latest changes. This ensures that electrical installations are designed and installed to the highest standards of safety and performance.